So the basic premise here is pretty simple. So if I have this graph here starting at 0, it looks like it goes till 4, and I'm interested in knowing the arc length, or maybe you can think of if you're going to walk that path, what distance would you walk? Or if you're going to if you laid a string on it and then stretched out the string on the x-axis, how long would that string be? Right? So pretty simple premise. How long is the curve, right? So what's the distance along the curve? Okay, so what do you guess? So what do you think this is? 8, 9, 10, 11, 12, 13? What do you think? How long is this curve? Who says between 8 and 10 units? Can you see the x-axis down there? Can you read that? What do you think? Between 8 and 10 units long? No? How about between 10 and 11 units long? Between 11 and 12? Between 12 and 13? What about the rest of you? Are you abstaining? Okay. So, again, it's like laying a string on it. It's like laying a string on it. And we'll just let it play. And then after you lay the string on it, stretching it out. The whole way, right? A lot longer than you thought, okay? So I think there's like 2 people that said between 12 and 13. All right, so anyway, so that's the idea here. So we want to find arc length. Okay, so if we want to, and more than that, we want to have an arc length function, right? So could we develop a function, say starting from x equals 0, that given any value of x between 0 and 4 would give us the length of the curve starting from 0 up to x, to any x value up to 4. So if we want to develop an arc length function, what do we need to do an arc length function? Quiz. Everyone write it down. Here's a quiz. See if you're ready for Friday. What would we need if we wanted to write an arc length function? An arc length function, say, for the length of the curve from 0 to any value x between 0 and 4. So this has been the theme for the whole first month of class. So let's see. Yes, sir, Walker. Rate of change of arc length. Is that so? That's what you should have written or should have been thinking. We need the rate of change function for arc length. Okay? Right, because when we wanted to get an accumulation of volume, what do we need? Rate of change of volume. If we wanted the accumulation of signed area, we needed the rate of change of signed area. If we want the rate of change, if we want the accumulation, the net accumulation of any quantity, we need its rate of change function, and that's going to be the key component of setting up the integral function, right? The integral function to get net accumulation, and then total accumulation if we want it. Okay, so let's talk about how we're going to get the rate of change. So there's kind of a process here, and it's similar to, we're going to take, so we want, say, to build a function for the rate of change for the length of this curve. So what do we do first? What do we do first in all situations? So there's a clue up there on the screen. Delta x intervals, right? We're going to split up our x domain into delta x intervals. And then we're going to imagine, always, like always, we're going to imagine x increasing through those intervals. And then what is our definition of dx? What's our definition of dx? Dx is always what? These are all key questions for your exam. How much x change is in the current interval, right? And is that a variable or is that a constant, dx? Variable. Is delta x a variable, or should I say parameter? So is delta x variable or not? Delta x. That's fixed, right? That's the width of our intervals. But dx is variable, right? It varies through each interval. So it ranges between 0 and delta x. So here it is, dx is ranging through the first interval. And then dx ranges or changes through the second interval. So it always has the minimum value of 0 in the current interval up to delta x in the current interval. So as x increases through the intervals, dx varies in each interval from 0 to delta x, and then it starts over. Now that's true for every single application we've seen so far. That's always true. So then what are we going to do? We're going to look at points on the curve. So if we want arc length, the next thing we're going to do is we're going to add points on the curve, okay, at the ends of the intervals. See that? Okay, so I'm just anticipating ahead a little bit. What is going to be our approximating element then for arc length? What's going to be our approximating element? What was our approximating element for volume? How do we fill up these empty shells? What kind of approximating element did we have for those? Right cylinders, right? Right cylinders. So we're not going to use cylinders here. Totally different ball game here. What are we going to use here as approximating elements to try to approximate arc length? What's that?
Straight lines.
You want straight lines. Yeah, like so segments. So we can use straight line segments between these points that we just found out. So we're a little, but we have a few more steps to do before that. So first we're going to think about dx, and we're going to think about that starting at each point on the curve. Okay, so it still has the same value. We think about locating it at the points, right? So let me show you that again. So we're going to let dx, it still varies through each interval, but let's put that vector, if you will, with its tail at each point. All right, and so then next we're going to look at the corresponding dy as we go through each interval. So dx, the same as before, but now dy is going to vary at a constant rate from one point to the next, right? So dy is going to vary with dx at a constant rate to form what we said, a linear segment. Okay, and so those linear segments, as we progress through the intervals, that linear segment we're going to call ds, right? So dx is taken, dy is taken, so we're going to use ds to mean the changing length of the segment from one point at the point at the beginning of the interval to in the straight line to the point at the other interval. So ds is a variable. You see that? So as we go through the current interval, dx varies horizontally, dy varies vertically, and ds varies along the straight line segment from the first point of the interval to the end point. Does it make sense? Okay, and so now we're going to leave a trail. We're going to leave a trail on those ds vectors. So you see that we've got done with the first interval, and we've left that segment behind. And now we're in the second interval, and we haven't quite finished yet. ds is increasing to that ending point, and then we get to the next interval. We always leave the completed segments behind. So just like we had completed cylinders and then the partial cylinder growing in the current interval, now we have completed line segments, right? And the partial line segment growing in the current interval. ds is a variable. So how do things accumulate? So they're going to accumulate through completed, or we'll have accumulation through completed intervals and then some accumulation in the current interval. And that's changing as x changes. So that's kind of our strategy here. That's what we're thinking about. And so then what was the big thing we needed? What was our thing we were after here? The rate of change of what? So what exactly the rate of, so in this scenario here, the rate of change of what? What do we want? He wants the rate of, she's saying the rate of change of ds. Agree? The rate of change of how that line is, that segment is increasing to the final point of the interval. Right, and so what would that be symbolically? No, symbolically. Symbolically, how would we represent the rate of change of this line segment growing. So what? It's the rate of change of S, the rate of change of S with respect to X. So it would be the rate of change of S with respect to X. Anybody? How would I write that symbolically? Okay, so that would be one way. What about with this notation that we have up here already? ds dx, right? ds dx. So this is what we're after. If we can find ds dx, we're home free because we know how to write a net accumulation function for any quantity whose rate of change that we have, right? So we're going to have the rate of change ds dx, and then we know it's kind of easy from there how we can set up the net accumulation function because we've been doing it all semester, right? Okay, so here's how we're going to find that. It's kind of a trick. So we're imagining, right, we imagine this triangle increasing through the current interval. And do you see that no matter what x value it is or what dx we have, we always get this, it's like a set of similar triangles. Do you see that? Because of constant rate of change. The ratio of dy to dx is the same. So that triangle, as dx increases, that triangle is always maintaining a similar shape to the one before. Okay? So what we want is we want to keep letting that thing increase until dx equals 1. So in this case, our delta x's are less than 1, so that means we have to kind of pretend we're still in this interval and let that triangle get really big until dx is 1, and then you'll see why this works, okay? So instead of going on to the next interval, we're going to continue in this interval and imagine that thing growing until dx equals 1. So I'll do it in, I wish I had another color, but I guess I'll go ahead and do it in black or blue. I'll do it in blue. Okay. So my blue triangle is going to be the one where that thing keeps growing until dx equals 1. And then it's going to be similar to the one we have, right? Or the one that I'm showing at the moment. It'll be similar to all of the triangles in that current interval. All right, so in order to do that, what did I just do? I just had our dx, dy, ds triangle. And I scaled it, or I froze it. I was thinking of it increasing, right? dx is increasing, ds is increasing, the whole triangle is increasing. But then I paused it when dx reached 1. So what scaling factor do I use to get from here to here? So what do I need to do to this triangle to get 1 for that base segment? What do I do to that triangle so that I get the triangle 1 here, the length of 1 here? How did I scale that triangle so that this is 1? Yeah, multiply by 1 over dx, right? Or you could think of divide by dx. So my scaling factor was 1 over dx, or divide by dx. Is it fair? So now what's my new length of my vertical change? dy over dx. Okay, and what's my new length of my hypotenuse, or my segment that's actually approximating the curve? Look at that. It's ds over dx. And that's what we wanted. So now we can write out what ds dx is. We can write out what the rate of change of ds over dx is. How are we going to do that? So what's ds dx? Use the triangle, right? Use the triangle. Go ahead. Yeah. Square root of, right? So we've got Pythagorean theorem, right? It's a right triangle, always. It's always this right triangle. And so ds dx. So the length of the segment in this triangle is our rate of change. So this is the triangle such that the length of that hypotenuse is the same as the rate of change always as it's growing. ds dx. Did you catch it? Does it make sense? So it's going to be square root of 1 plus okay, did I lose you? Does it make sense? Okay. Well, now I want to take my ds dx and put it on this triangle that I've got for the approximating arc length, that segment, and I want to scale it back. All right. Now I want to multiply back by dx. I'm running out of room. So now I'm going to take that one, I'm going to multiply back by dx to get back the original triangle, which again, this is now like any triangle as dx is increasing, right? Think of dx is increasing through the interval, this triangle is growing, maintaining its similar shape, but I can write it in a different way now that I know this is times dx. Okay? So rather than, so when I do that, when I'm back to dx here, okay, and then I could write this as dy dx times dx, or what, m dx. Right? See, the whole time we're maintaining that relationship of what? dy equals m dx. It's all based on that. That's why we get the similar triangles. dy and dx are always maintaining that same proportion, so we get all the similar triangles. Okay. So if I change by dx, how much does my height change? By m dx, right? M dx. And now, how much does what's our little change in approximating arc length? So right there, this is the key right here. It's going to be our ds dx times dx. So this little length right here, I don't want to get too messy here, so I'm going to put a star, because that's, and I'll do it over here. Some room here. So that length is the square root, so ds is the square root of 1 plus dy dx quantity squared dx. Okay, what is this right here? What's the square root of 1 plus the square root of 1 plus dy dx squared? What is that? Which is? It's ds over dx, which is our rate of change, right? Rate of change of the approximating segment of the arc. Approximating length of this. So it's approximating the arc length with a segment, right? So it's the approximating length. No, it's of the arc. It's the rate of change of the length of the segment, which approximates the arc length, right? It's the rate of change of the length of the segment, which approximates the arc length. And so then this whole thing then times dx is what? That's the changing length of the approximating segment in the current interval, right? That's the length of the approximating segment. In the current interval. So then the last thing is, what is dy dx? It's the same dy dx as always. So what is dy dx? It's the rate of change of the function, right? It's the rate of change of the function that we have for which we're trying to find the arc length. So that we started with this blue wavy function, right? This blue curvy function. That has a rate of change function. And it's dy dx, right? Its rate of change function is dy dx. So that's all that is right there. That's the rate of change of the function whose arc length we're measuring. Or we're calculating. Okay, so then what would be the accumulation function, the net accumulation function of arc length? Say starting at 0.5. So say we're going to start accumulating this, or what was this? Negative 1.5. Okay, so this in this video start at negative 1.5, and so could we write the net accumulation of arc length starting at negative 1.5? How would we do that? Or give it a try. Give it a try. So we want to call that function s. So ds was a little bit of arc length, right? As a little segment, right? As a little segment. So that function will be s. So the book, and so if this original function, let's say this original function was f, okay? So the function we were looking at was f, okay? So what we'll say is this is the arc length of f. And the book uses a two variable, or a kind of a one variable, but also with x. So they'll say this, and that just means x is our independent variable, but then we want the function starting at a. So really, we haven't included that before, so this is also, that's consistent with what we've done so far. Knowing what a is, right? Just knowing what a is for our particular function. So either of these are acceptable. In the second case, it just has to be explicit that you know what a is. In the first case, you actually include it. Okay, so what I'm saying is, what is s of f of negative 1.5 x? So this is our accumulation of arc length function. Net accumulation of arc length starting at negative 1.5. Anybody think they got it? What would it be? This follows the same principles that we've done before. Somebody new? Yeah. What do you think?
Would be the integral from negative 1.5
Okay.
to
2x. Good.
of the square root of 1 plus dy over dx squared dx.
Okay. And then if we particularly, I told you that our function is f here, then we could put that in there. So as another, so we could say what the rate of change of f, and rate of change of f of something else, not x, something else, right? But then we want to do what to that? Square it. And then that was our rate of change, right? And so to get a little bit of approximating arc length, we're going to take the rate times the change in t, right? The rate times the change in t gives a little change in s, right? So you could put, so there's different notation you could put here. You could put df dt, the r sub f of t. You could put f prime of t dt, right? Those are all derivative notations that are legitimate, okay? And then also, we could also put s sub f of just x, knowing that we mean the net accumulation that starts at negative 1.5. Okay? Okay, does anybody have a question? So what, we build up the rate of change of arc length, and so then everything else is the same. We're going to have our starting point for accumulation. We're going to do the integral of the rate times a little change in our independent variable. Gives us a little change in arc length, and then we're going to accumulate all those little changes starting from negative 1.5 up to x. Okay, so use function notation to represent the whole arc length shown, right? So from negative 1.5 all the way to 1.5. How could you use function notation to represent the entire length of the curve, some of which I've erased over there on the left, but it's still there. So all the way from x negative 1.5 to 1.5, how can you use function notation to represent that whole length of curve exactly? This is important. Important that when we say function notation, you know exactly what we're talking about. Are we talking about writing an integral? No, what are we talking about? So somebody knew. What would function notation be for the whole length of the curve from negative 1.5 to 1.5? Yeah. Mm-hmm. Right, that would be the function notation. So that last question I asked, she said this: S sub f of negative 1.5 to 1.5, or just S sub f of 1.5, having defined that function as starting at negative 1.5, okay? That's what we mean. So that function notation represents, that value is the whole length of the curve from negative 1.5 to 1.5. It's a lot easier than writing out this whole integral again, isn't it? And it has the same, it means that value of the length. So we can give an answer even though we don't know the number, right? So we can give an answer. What's the length of this curve? Well, it's S sub f of 1.5, where S sub f is this function over here. So it's very convenient in that way. Okay, so let's look at an example. Any questions on the derivation of the rate function or the arc length accumulation function?
Well, just to be clear,
Sure.
what's in the brackets there, the rate sub r sub f t, that's dy dx.
Yeah, right. So dy dx is just the rate of change of y with respect to x. That's our derivative of this function. So we have lots of notations, ways to say that, right? F prime of t, df dt, r sub f of t are all the derivative of the function. Yeah. dy dx is another one. Yeah. All mean the same thing. Okay, so I got an example here. This one. So here's one. Here's the function. I don't want to say it. A polynomial times e to the minus x. Okay? A polynomial times e to the minus x. and I'm starting from x0. So what I want to do is I actually have this. I'm going to put it on the dot cam. I'm going to do this with a string, and then we're going to calculate it with GC and see how close we were with the string. See how my dexterity is. Okay. So we want the, where is it? How do I get the dot cam? Yeah, there it is. Okay. So here's the dot cam for this curve that I have showing on my screen, and I'm going to try from 0 to 5, okay? So let's watch my butterfingers here. So I'm going to put it on like this. And once I get some of it, I can just kind of pinch it there, and I don't have to worry about what I've already done. So come down here like this. So you get the idea of what I'm doing here, and I'm going to just go to 5. This 3. I think right there. Okay? So I'm going to hold that with my thumb where I ended up. And what would you guess I got? 11.8 or something? 11.8? Okay. So how will I use GC to find out exactly what that arc length is? I want to know exactly what this arc length is from x equals 0 to x equals 5. We think it's using the string, we got 11.8. So what will I put in GC to do this? What should I do first? Okay, I'm hearing derivative or rate of change. Okay, well, of what? Of f of x? Okay, well, I can, so are you saying you want to do the product rule and find it? So GC can do that for us. GC can do that for us. I could just do, so I can say rate of change. Rate of change of f of x, and then we could say equals, and then if you go up here to the math menu, you total derivative, and then f of x. Okay, so I've just defined the rate function. So I've got the derivative of f as now is defined as r sub f of x. What else do I need to define? Yeah.
Well, you could just do like a separate formula. So let's say like s of u equals the integral from 0 to 5.
Okay, so think about an s of s sub f, right? Because it's going to be like the.
Oh yeah.
So yeah, that subscript is referring to the function which we're trying to get the length of. Okay, so s of f of what?
If we're trying to find the exact value, we would do s of. Would we still use x or would we do 5? We would do x, right? Or if we can
What's a stronger thing to do? X, because then all we have to, right? So then we get all the values of arc length, and then we can just pick the one we want.
Okay.
So let's do the function. The function is always a stronger choice. Okay.
Then we would do the integral. From
Integral.
0
Okay. Control Shift I.
0 to x.
0 to x.
And then we would do the square root.
Square root.
1 plus
1 plus.
d f of x over.
Okay. So don't we want to do the product? Don't we want to do the product rule, and then square that, and then put that in here?
Well, we already had it in function notation.
Oh, see, function notation. See that? It's really handy. No, we don't want to do the product rule and square that. I mean, even if it's not hard, it just takes a lot of writing and takes a lot of time. Then I got to put it down in here. Okay, so function notation is your friend. Okay, it's your friend. It saves you time and it just has a lot of advantages. So instead, you want to do what?
We could just use
R sub f of x. Need something else. Need something else, right? And then square that.
Then change the dx to dt.
And change the dx to dt. What do you think what he did? Does that give us the, and we could have written that as s sub f 0 comma x, right? Same thing, just knowing, we can write s sub f of x just saying, okay, we know that this particular net accumulation function starts accumulating at 0. But the alternative notation would be to do s sub f 0 comma x, okay?
Then if we want like the 11.8 or anything close to it, we just plug in 5 for x.
Okay, so now we want to, right? If we want to test your teacher's ability to put strings on curves, it would be what? S sub f of, here's the test. Pretty good. Off by 0.2, right? Off by 0.1865.
Exactly.
So pretty good, right? So we did pretty well. So, and then that gives us the exact version. And then this now is, we can get a function for any arc length starting from 0. So if I wanted the arc length only up to 3, I would do S sub f of 3. And if I wanted to use this function to get me the arc length, say from 1 to 4, how could I, instead of building a new function, how could I use this function to get the arc length from 1 to 4? Right, so it would be all the arc length up to 4 minus all the arc length up to 1. So,
Or you could just change the 0 to 1.
right, I could make, so I could start a new function which would accumulate starting at 1 and then make x equal to 4, and that would do it. Or I could use this function and do final minus initial, right? Final minus initial. So I'm going to do that. Either way works.
Okay, so can you do it if you have like the 2 where you start and end? You can do s of f of 1 comma 4 and that'll give you the same answer.
But I'd have to define that function starting at 1. I've only defined this one starting always from 0. So yeah, I'd have to define a new function where it would be integral from 1 to x, and then I could do that. Yeah. Okay, so now this. Okay, great. So now what she's saying is, what if we did this? Let's see if it'll work. Do a comma x, and then make my function be what? A.
There we go.
Yeah. Then you can do whatever you want, right? But somehow this doesn't work until I do what? Now here I got to go 0 comma 5. There it is.
So then if you did that, then you could do like 1 comma 4.
So now, and I should get the same thing that I did before. Was it 3.65 or something? Yeah. You guys are smart. What's that? No, yes I will.
So far, the one has put us in that.
Okay. Any questions on arc length? So maybe a couple questions on the basics of this. If you got the basics of this, and then there's some easy homework problems in the book. Not easy, but they're straightforward. Straightforward. If you see exercise set 8.4.1, just 4 functions and just a set of exercises here to do. They gave you the interval, x equals 2 to 5, 1 to 4, negative 4 to 4, etc. So if you want to practice a little bit with that, that would be good practice for the exam. There would be nothing on the exam beyond the scope of these questions right here, okay?